Recall that whenever an object is undergoing translational motion, that object is said to have kinetic energy, and the quantity of kinetic energy is given by the following equation: 1/2 mv squared, where m is the mass of the object, it's the inertia of the object, and v is the linear velocity of our translating object. So this is known as translational kinetic energy of our object. Now, in the same analogous way, we can also determine a formula for the kinetic energy of an object undergoing angular motion about a fixed axis. So let's suppose we have the following two-dimensional rigid object, let's say our rigid disk. And the disk is rotating about an axis of rotation that passes through the center. Now, this disk is composed of many tiny particles, each with mass mi and each with angular velocity. Now, the angular velocity of each of the particles that compose our object is exactly the same. The angular velocity remains constant, and each particle that composes our object rotates about the same exact axis of rotation. Now, if we take the product of the angular velocity of our particle and the distance from that particle to our axis of rotation, if we multiply omega multiplied by Ri, that will give us the linear velocity of that particle. And if we want to calculate the kinetic energy of that individual tiny particle with mass mi, well, I simply use this formula, 1/2 mi vi squared. So that's the kinetic energy of that single individual tiny particle. Now, what about the kinetic energy of the entire object? Well, to calculate the total kinetic energy, I simply sum up the individual kinetic energies of every single tiny particle with mass mi and linear velocity vi. So the total kinetic energy is equal to the sum of 1/2 mi vi squared. So now I want to express this equation in terms of angular physical quantities. So I replace vi with this formula. So angular velocity multiplied by I. Now, my omega becomes squared, and this term also becomes squared, so I'm left with the following result. So notice I have the omega squared that appears on every single individual term. It's a constant, so that means I can take it out of my summation equation to obtain this equation. And also notice that the 1/2 also appears on every single term. So that means I can take it out of my equation and get the following result. So I have 1/2 multiplied by this sum multiplied by my angular velocity squared. Now notice this sum, mi/ri squared, is simply the rotational inertia of that particle. And if I sum up all the rotational inertias, all the momentum of inertias of the individual object, individual particles, that will give me the entire moment of inertia of my two-dimensional object. So that means I can replace this entire term with simply I. So I get that the rotational kinetic energy of the object that is experiencing angular motion about a fixed axis is equal to 1/2 I omega squared, where I is the rotational inertia of the object and my omega is the angular velocity of our object. So we see that the form of this equation is almost identical to this equation, except we replaced the physical translational quantities with the physical angular quantities. Now, when the object is undergoing angular motion, that object is experiencing a change in rotational kinetic energy. So it's gaining kinetic energy. So that means there must be an energy transfer that is taking place. Energy is inputted into our rotating object by some force. And that means work must be done on our rotating object. The question is, how much work is done on our object? Let's suppose we have the same exact object. We choose a particle with mass mi, and a force acts on that particle over a very small, infinitely small distance, dl. Now notice the distance from this particle to the axis of rotation is given by r, and notice that the force acting on the object, on our tiny particle, is perpendicular to this distance r. So that means the work done is equal to the integral of this force multiplied by the distance that our object travels, dl. Now, recall our relationship between our L, the distance it travels, the angle theta, and our distance r. So d theta is equal to dl divided by r. And that means we can represent dl as simply the product of r multiplied by d theta. So we can replace dl with r multiplied by d theta. And recall that the torque created by force is given by the following equation. Torque is equal to the force acting perpendicular to the distance r. So we can replace this entire form with simply torque. So we see that work is equal to the integral of torque d theta. So let's suppose its initial angle is theta 1 and its final angle is theta 2. So that means we can define the definite integral from theta 1 to theta 2 of the torque and d theta, where d theta is simply the infinitely small change in the angular position of our object. And this is the work done by the torque to rotate the object from theta 1 to theta 2. Now recall from Newton's second law of motion for angular motion, the torque is equal to our rotational inertia of the object I multiplied by its angular acceleration. And angular acceleration is simply the derivative of our angular velocity function with respect to time. Now, we can represent this equation in the following way. So I multiplied by our derivative of the angular velocity with respect to our angular position multiplied by the derivative of the angular position with respect to time. So we simply add a d theta on the bottom and a d theta on the top. Notice that these can cancel out and we get back this term. So these terms are exactly identical. And so that means because this quantity d theta divided by dt is simply our omega, our angular velocity, the derivative of our angular position with respect to time is equivalent to angular velocity, we can replace this term with omega and we get the following result. Torque is equal to I, the moment of inertia, multiplied by omega, multiplied by this quantity, d omega over d theta. So we're taking our derivative of our angular velocity with respect to our angular position. So now we can take this equation, which we have here, and plug in this entire term into torque. So notice, this is a constant, so we can take that constant out. We get our moment of inertia multiplied by the integral from our initial angular velocity, the final angular velocity, our angular velocity multiplied by infinitely small change in the angular velocity. So we take the integral, we get our angular velocity squared divided by 2 multiplied by I, our moment of inertia, from our omega 1 to omega 2. So we evaluate the integral and we get the following result. So this equation, we labeled it as equation 3, gives us the amount of work that is done on our object by the force that increases our rotational kinetic energy of the object.